Hello, my name is Carl. Welcome to my workshop and welcome to my YouTube channel. In this video we're going to be looking at how I attempted to make a test nut for the Harrison mill, the 5 acme test nut for the knee lead screw. And I had a few problems doing that, and a bit of a schoolboy error on my part was the cause of the problem that I had. And so we'll look into that and see what I did wrong and what I'm going to do to rectify that. We'll also be looking at some of the work that I've done already on the Harrison milling machine refurbishment, a little bit of an update on how far I've got or an insight into where I'm going, and then we will close out the video. So without further ado, let's get on with it. Hello people, you join me in a position ready to start trying to cut this 5 acme test nut. So we have got the lathe set up. Let me show you what we've done. We've got the 63 tooth gear in the back in the change wheels. We are set to L2 on the feed gearbox, which is the correct setting to cut the 5 TPI acme thread. We've got our lovely new acme threading bar in the holder that we made in the last video. We've got a piece of acetal or Delrin in the chuck, and we've bored this out to the correct size, which is 0.905 inches. As I showed you, I think it was in Mill Resto Part 4B. Or potentially Part 4A, I can't remember now, but go back and have a look anyway, it's worth a look. We've got the top slide set over to 14.5 degrees. I appreciate that that threading bar is carbide and could probably cut straight in without having to be set over like this, but I want to do that because I just want to, because it's such a big tool, it's almost like a form tool, I just want to keep the cutting on this edge to try and minimize the tool pressure basically. So this is set over to 14.5 degrees. I've got the clock gauge set up on the tool post so that I can read directly the movement of the as I feed it in, or feed it this way towards us actually. The reason for that is that there's because this is now the hypotenuse of a triangle, we've got a trig issue here, a trig problem, which will give us the, if we do the trig problem, it will give us the actual movement that this is moving through linearly rather than on this hypotenuse. And I'll show you how to do that, how to work out the value on the whiteboard later on, because it is quite interesting. But the easiest way to deal with it for practical purposes is to set up a clock like this, so we're reading directly the linear movement in terms of a reading on the dial, kind of like an analog DRO, I suppose. And I still haven't replaced that the glass front there, the bezel, since the last time you saw it. So bad habits, terrible. Right, so we're in a position now really to oh, I forgot to tell you as well that this is square to the job. I set that up with the old the fishtail tool, so we're basically ready to go. What I need to do now is, once I get the lathe started up, is to engage the half nuts. Once the half nuts are engaged, they will remain engaged for the duration of the entire threading job, because this is a metric lathe and we're cutting an imperial thread. So we'll be using the good old switch here that I showed you in the video on the VFD. So this is the forward, reverse and stop switch. So we'll be using that with this rapid deceleration facility to stop the tool once it exits the bore on the back side there. We'll keep an eye out for it exiting. We will stop the tool. We'll wind the tool out using the cross slide, and then we'll reverse using this switch. Once we've reversed back out, we'll wind the tool back into position, back into 0 on the cross slide, and put some more feed on with the top slide, and so on and so forth until we get to the point where we can actually try the lead screw in there. And you'll remember from part 4A and potentially from part 4B as well in the Mill Resto series, that what we're looking for is half the pitch plus 10 thou as the depth of the thread. So the pitch is 0.2, so we're looking for 0.1 plus 10 thou, so 0.110 is what we're actually aiming for. And once we get to that on the clock, we'll give it a go, and we'll go from there. We'll see if we need to depth it a little bit more. And yeah, so basically this is an experiment to work out exactly how much we need to go with the depth, and just to make sure that the tooling all works. So we'll get on now and we'll start cutting this thread. Okay, so you've just seen me bore this out and put a thread in it. So after putting the thread in it, I took it out of the chuck. Well, I tried it actually. I tried the lead screw in it in the chuck first, and it didn't fit. It screwed in maybe 2 threads and then stopped, which immediately made me think I've got a pitch error here. So I sectioned the test nut to have a look at it to see if I could find out what the problem was, and it's cut a nice thread in it. If I zoom in, you can see that it's a nice thread. It looks all the correct proportions, but you can see here, look, there's a bit of a groove there where I was trying to thread the lead screw into it. It's bound up. One of the key dimensions is incorrect, so I measured the pitch across here. It should be 0.2 of an inch. It's actually 0.212, 12 thou over. So that makes it, if you do 1 over the pitch, gives a TPI. It should be 5 TPI. So this should be 0.2 for 5 TPI. 0.212 gives us 4.7 TPI. So basically that pitch error can only have been caused by a gearing error on the machine. So I looked into that and I discovered that what I thought was a 63 tooth gear, the white one that we made the adapter for in the previous video, the last video, was in fact a 60 tooth gear. So no surprises that we produced, or I produced, a thread of, you know, nice proportions and a good thread, but just the wrong pitch and the wrong TPI therefore. So never mind, back to the drawing board. I have a 63 tooth gear on order. So when that comes, we'll be able to do this again, but correctly. But having said that, I am pleased with the way it's turned out. Otherwise, it's a nice thread. It's well proportioned, other than the pitch. It looks good. I think that bodes well for doing the same in the bronze. Well, not the same in the bronze. Can you imagine how annoyed I'd have been if I'd done that in the bronze? Like this, but correctly in the bronze. Okay, so I told you that I was going to show you all about the trigonometric issues when you're dealing with the top slide set over to half the thread angle when you're doing threading in the lathe. So I'll just have a quick session in front of the whiteboard with you now and explain that to you. I'll try not to take too long or to labour the point too much. So basically what we've got here is a diagram of how we've got the top slide set up. So it's set over at the angle of half the thread, which is half the thread angle, which is 14.5 degrees. So this here is the hypotenuse of a triangle, as I mentioned. So we've got a right triangle here. So in trigonometric notation, we're going to call this the hypotenuse. This is the adjacent in terms of this angle, and this is the opposite. So the sides that we're interested in of this triangle are the hypotenuse, which is our top slide movement, and the adjacent side, which is the actual depth of thread movement that we want to get the correct depthing. Now, trigonometrically, the secant, which is a trigonometric ratio, defined as the hypotenuse divided by the adjacent, as I've written here, or it also can be defined as the reciprocal 1 over the cosine of this angle, and the trigonometric ratio cosine is the adjacent over the hypotenuse. So the secant of this angle, which I'm calling small a or lowercase a, multiplied by the distance that we want here, gives the amount of movement that we need to move the hypotenuse, because this has to move further to get the same translation that you would get if you were moving along this line, along the adjacent line. So the secant of angle A multiplied by the adjacent side A gives the hypotenuse movement. And the secant is 1 over the cosine, or the hypotenuse over the adjacent. But we don't need to worry about these distances. We can just find out what the secant of this angle is and multiply the thread depth, which is represented by this line, by the secant of this angle. Now most calculators don't have a secant function, so what you can do is, as I've written here, is 1 over the cosine of the angle. So I've written here movement of h to achieve a, so h travel, the travel of the top slide, would be a times 1 over the cosine of 14.5, the angle of or half the angle of the thread, which gives us a times 1 over 0.968, which is the cosine of 14.5, and that comes to a times 1.033. So to get the movement on the of the top slide, or the hypotenuse, that will give us the equivalent translation along this along the adjacent side, or the depth of the thread that we want, we have to multiply the depthing by 1.033. So to show you an example of what we were doing earlier, this would be the 10th thou cut that we were taking. Multiply that by 1.033, and we would have to put a cut on the top slide to get the same translation. We'd have to put 0.0103, so 3/10 on top of this, basically. So you can see here that you're going to be talking about splitting tenths with the top slide. So that's why we have our clock gauge, which is giving us a direct reading of how much this is moving. So we can actually translate this by the amount that the clock gauge is showing that this is translating, because we get down to these kinds of figures. So I think it's important to understand why we do this and what the trigonometric identities are behind all of this when we put that clock gauge on, so we know exactly what the principle is around why we're using that clock gauge. And obviously it's this way around because it's an internal thread, so we're feeding this way, and we've got the top slide set over in this orientation. If it was an external thread, then it would be the mirror image of this. This would be this side. So there you go. I hope that's been of some use to you, or at least has given you a little bit more understanding of why we were doing what we were doing. So this is the motor out of my Harrison milling machine. I'm handheld here, so the usual disclaimer with regard to motion sickness. When I removed this motor from the machine, it was absolutely filthy. It was so black you could hardly see what it was supposed to be. And I removed it and pressure washed it first of all. And then after pressure washing it, I dismantled it completely and dunked everything in the solvent tank and cleaned it all out. And then I replaced the bearings and I rewired the stator to delta for a 220 volt VFD drive eventually when it gets fitted back into the machine. It's flange mounted, so this flange here bolts up to a 1/4 inch thick steel plate which is inside the machine, and then you have the belt drive from the pulley here. And Paul from Haxby Shed, if you're watching, I changed the bearings, so I know yours is a bit noisy. Mine was as well before I replaced the bearings, and now it's virtually silent. So this is a Brook Crompton motor. Handily the data plate is upside down. It's a 2 horsepower, 3-phase, and it's 2,840 RPM, which means it's a two-pole motor on 50 Hertz. There's not an awful lot else to show you about it really. The original bearings that were in this were greased with grease nipples, as you can just about see one there with this red plastic cover. What I replaced them with shielded types. They, despite the amount of grease that was on the machine and in the machine, I think they were the only things in it that had never been greased. They were almost completely dry. So it now has a nice new set of shielded, maintenance-free bearings. So there you go, that's the motor. It doesn't have much in the way of an integral cooling fan. So I'm thinking that when I have this run from the VFD and it's running at the slower RPMs, I may need to fit an external fan, something like a computer fan in the back, perhaps bolted onto the back of the motor. And I would drive that from one of the auxiliary outputs from the VFD and set it so that in the programming, when the motor's running below a certain frequency or a certain RPM, the fan switches on. So we'll take a look now at the feed gearbox. Right, so before we have a look at the gearbox, the feed gearbox, let's have a look at the drawing. So we can see on the left hand side we have the 8 horsepower Brook Crompton motor, which drives the feed gearbox and hence drives the table lead screw to give the feed. What I did to this was I changed the bearings inside it and I rewired the stator to delta to operate with a 220 volt VFD. I also painted the exterior, removed all the old paint off it and gave it a new paint job. And that drives through this pinion, which is held in place, or which is keyed to the shaft by this key, and it's held in place by a 1/4 UNC screw through the shaft and through this spacer or washer here. This is a seal which prevents the lubricating oil inside the gearbox from leaking out through the where the motor penetrates the box. And here we have a spacer. So this pinion drives this gear here, which is keyed onto by the spline, which is keyed to this shaft by the spline here, and the shaft is supported by these 2 roller bearings, which I've replaced as well. And then that shaft runs through out to the exterior of the gearbox and drives through this change wheel arrangement here, and these are Myford change wheels, so they're quite easily available, onto this top shaft, which has a spline, and this worm here is splined onto the shaft and supported in these 2 bearings, which have also been replaced. And that worm drives this worm wheel. Now this worm wheel is actually the lead nut. Inside there is the lead nut thread, which is 3/4 by 6 TPI, if memory serves, acme, and right hand acme. So that's supported again by these 2 roller bearings, which have been replaced, and there's a big spacer at this end which holds the whole assembly together. So the way that this works is that the lead screw runs through here, obviously, and is attached. This is attached to the table. So if you have the lead screw unlocked by a locking dog, which is on the handle, you can then rotate the lead screw, and it runs the nut will run along the lead screw, and by virtue of the fact that this is attached to the table moves. But if you actually engage the mechanism on the lead screw on the handle, that then locks the lead screw up and it can't rotate. So then when this turns by a reason of the motor, then it runs itself along the lead screw and the whole table moves along the lead screw. That's how the power feed works. So as I say, all these bearings have been replaced, everything's had a good clean. Any damage or nicks on the gear teeth was blended out with a diamond file. And I'll now show you the completed gearbox. Before I do that, I just want to mention that these two change wheels are held on by these little knurled nuts here, and these have got like a cross cut in them and a small grub screw to lock them in place. One that once they're on, you tighten the grub screw, just give it a nip, and it opens up the gap, the notch in the nut, and locks it up. And these were missing when I got the machine. I had to make these, so I'll show you those in a minute as well when we look at the gearbox. And what I'm going to do inevitably is, or eventually, is have these two gears like a 1-to-1 ratio, basically, because I'm going to run this from a VFD, so I'll be able to basically adjust the feed based on the frequency of the output into the motor, rather than having to swap these change wheels around to change the ratio of the drive and hence change the speed of the feed. So I've shown you the drawing of the feed gearbox, and I've given you a brief description of its operation, and I'm going to show you it. So you've all seen this cardboard box. No doubt you've noticed it sitting on the end of my second bench, and you're now going to see what's inside it. So it is the feed gearbox and the Griffin motor that drives it. So we'll take this out of the box now and we'll have a look at it. So here you would have the feed gearbox and its drive motor. So this is an 8th horsepower Brook Griffin motor. Griffin was the name that Brook Crompton used for their range of fractional horsepower motors, and I think they still do use that name actually. So this is an 8th horsepower motor, as I said. I've changed the bearings in this, and I've rewired the stator for delta for a 220 volt VFD, which is going to be driving this when it's assembled back onto the machine in the fullness of time. Now, I didn't have much data on these motors. I couldn't really find any drawings of them, but it was a fairly simple thing to take apart, and it's all 2BA stuff and 4BA. The hardest part was removing the bearing at the front end. I had to grind away at the cage and split it to get it off, because there was a kind of a part of the fan that stopped me from pulling it off with the puller. I couldn't get the legs of the puller behind the bearing, if you like. But other than that, it was fairly straightforward. This was covered in horrible Hammerite grey paint that basically resisted every single attempt that I made to take it off. The only thing that took it off in the end was sodium hydroxide. Oven cleaner basically is what I used, and I put it in a vat of oven cleaner. I painted it with oven cleaner and left it in a tub overnight, and the next day when I came in, the Hammerite just slid off. So that worked really well, and I used that method for the rest of the box as well. The only thing you've got to be careful with using sodium hydroxide to strip paint is it really attacks aluminium. It will corrode it ferociously before your very eyes. So if you are going to use it to strip paint, make sure that you've thoroughly masked off any aluminium components that you might have as part of the assembly. So this machine portion here of the gearbox, this flat with this dowel on it, this is where it attaches to the table itself, and you can see inside there is the lead nut for the table lead screw, and that, as I showed you in the drawing, has got a worm wheel integral with it, and that's driven by a worm, which is the worm which is on a shaft, which is transverse to the actual lead nut, and that's driven from the motor through the a gear inside here, a pinion and a gear, to some external change gears underneath this cover, and then up to the worm and then onto the lead screw, lead nut rather. So that's how that works. And I painted this gearbox with Paragon Harrison Grey, and I used their primer to undercoat it, and it worked really well. I'm the world's worst painter, but I think it came out nicely. And I would say that this gearbox and motor assembly is kind of an exemplar really of how I want the whole machine to look when I finally finish this refurbishment. So I'll spin it round now, and I'll give you a look at these change wheels and the retaining nuts that I made for them. So this is the change wheel cover here, with its oil level warning sign. It's scrubbed up beautifully, this thing. It was really dirty, but I cleaned it all and took all the old paint off, and then repainted it, as I mentioned, with the Paragon paint. So we'll take this cover off. These are just two captive knurled bolts, if you like, that hold this cover in position, and then it comes off. So there you would have the change wheels. So you've got your drive from your motor coming in to the back of the gearbox. It transfers over to a gear from the pinion on the shaft of the motor to a gear, which then drives the shaft that this gear is on, and then that drives back up into the gearbox onto the worm, which is on this shaft, and that drives the lead screw. So you can see on these nuts there's unnecessary zoom there. I had to make a cut in the side of them, in the through the edge, with a slitting saw, and then there is a grub screw through here which opens up the slot basically, and makes the thread grip onto the thread on the end of the shaft. It's a 9/16 UNF, the thread in there. So I made these up on the lathe on the Harrison. I knurled them, and then I made the slot with a slitting saw on the mill drill. So I'll just get the correct size Allen key now for these, and I'll whip one of these off and I'll show you them. So I have a 3/32 socketed Allen key, and these it's not going to play a ball, is it? No. Right, let's put you down for a second and we'll get this off. These just need the very slightest nip to lock, and you can see there it's already wanting to turn. So we'll get this off, and I'll show you one of these nuts. So there we go, that's what they look like. 9/16 UNF thread inside it. If it'll focus, which it has, there we go. And slot cut in the periphery, basically almost to the center, with a slitting saw, and then the grub screw through the front, which bears against the slot. So when you screw this on to the thread on the end of the shaft there, that grub screw opens that slot up very fractionally. It's like a flexure basically, and that locks the thread in position, so this can't come off and you can't lose your change wheels. So I just a bit of knurling and a bit of slot cutting and some threading, and I ended up with a couple of these. Right, so if I take this change wheel off, these are Myford change wheels, as I mentioned to you on the section when I was showing you the drawing. This is a 52 tooth. These are the only ones I've got, but they are easy to get, being Myford parts. So I can set up a ratio here and just leave it undisturbed and control the feed rate using the VFD. So what you've got here is a BSP plug, which is where you fill this with oil. It's Vactra Extra Heavy, which I believe is not too dissimilar to VG220, which is what I'm going to be using. It's a gear oil. Here's your sight glass, so you know how much oil you've got in there. and then you can see here the end of the shaft with a keyway on it, with a key rather, that mates up with the keyway in the change wheel. So behind these cover plates are the bearings, and it was quite interesting to dismantle this unit because the shaft had to come out and the bearings had to come out in a certain sequence and be put back in a certain sequence. And I used to take a lot of photographs and do a lot of write-ups on the MIG welding forum. So I'll leave a link to the post that I have on there for my Harrison Mill refurbishment, and there's a great deal of information and photographs and write-up on that particular website about this gearbox and how I rebuilt it. So I'm certainly not going to take it apart to show you now. So you can go onto that onto the MIG welding forum and read up how I dismantled and rebuilt this and the trials and tribulations that I had to do that. And also I've written up on there about how I made these, and I also had to make an arbor for my slitting saws because I didn't have one before I could cut that slot, so that's on there as well. So that's basically the gearbox. There's not an awful lot else I can show you. There's the other side of the lead nut, which, as I say, has got that worm wheel on it that's driven by the worm inside the box. So I'm looking forward to the day when this can go back on the machine, as you can well imagine. So we'll put this back on. These are meant to be lubricated with Vactra Extra Heavy or VG220, as I will be using. Finger trouble now, I can't get it back on. I'll put that back on off camera. It's very difficult trying to do it on the camera, but anyway, I hope you've enjoyed that little insight into the progress that I've made so far with this milling machine restoration. Well, we've come to the end of another video. I really hope you've enjoyed it. It's been a little bit bitty, I think, and obviously abortive with trying to manufacture the test nut, and a little bit disappointing, but not to worry. I found out where the problems lie in the process, and at least I didn't do it in the bronze, which is the main thing. So next time you see me, I will be able to cut that thread in the bronze with some level of confidence and satisfaction, I hope, as well. I'm going away to work in the next few days, so this will be the last you'll see of me for maybe 3-4 weeks now. Try and keep the cheers down to a dull roar. I'd just like to thank everybody that's come along and subscribed to my channel in the last week or so, or the last 4 weeks in fact, but especially since the last week. I've had a massive influx of subscribers, and I'd like to say a huge thank you to every single one of them. It really makes it for me to see other people enjoying this and coming along and watching what I'm doing and commenting and giving me hints and tips as well. And hopefully you're getting something out of this, and it's becoming a bit of a repository of engineering information for other people. If one person learns one thing from any of all this, then I'll have served my purpose. That's the way I look at it. And I'd like to say a very big thank you to Paul at Haxby Shared as well. He's just got the universal version of the Harrison milling machine that I've got, and he said some really nice things about my videos. They've helped him in the sort of the refurbishment work he's doing on his own machine, and he gave me a shout out on his channel, and that has really helped me pick up some extra subscribers. So thank you very much for that, Paul. Now, I hope you all have a fantastic Christmas. I don't know if I'll be able to get a video out before Christmas. I'll certainly try to, but we'll see how it happens. You know what these things are like. You get towards the festive season, and you have to put certain things on hold. So, but anyway, I hope you have a great time, and I'll see you on the next video.